Hello guys, so welcome again to our another VHDL lesson, interesting design as usual. We have now the 4 bits by 3 bits binary multiply. We have done this in the course, in our lectures, okay? So you have now two numbers. One is 4 bits, which is basically B, and the other one is 3 bits, which is basically A, okay? And the output, as we checked, was 7 bits. And why is that again? Because the maximum number is 7, with 111, and the maximum number of B is 4 ones, which is 15. 1 1 1 1. And when you multiply 7 by 15, the output will be basically a number that is represented in 7 bits. I think it's 105. Okay, good. So the design we explored, we said that if you go in as a straightforward approach, you will have a disastrous, consequences, because here you have 7-bit inputs. So you have 2 to the 7, 2 to the 7, to the power of 7 combinations in the input. So you have a 128 combination. So you will have very big truth table, very long truth table. Okay. And you have also 7 outputs. So you need to do the Karnaugh maps for 7 times. And each time you will have a Karnaugh map that is, seven variable Karnaugh map. So if you have 5 variable, you have a Karnaugh map with 32 cells. With 7 variables, you have a Karnaugh map with 128 cells, you know. So that's basically infeasible, or impractical, we can say. And of course, error prone and anything bad you can imagine. Okay. So we think a little bit, and we discovered that based again on the multiplication operation, we can use others. You can use the 4-bit binary others that we used before. Okay. And this was the resulting design. Okay, let's get close into it with our details, which we explored in the lecture. So here is a design again. Okay, and we can even get this bigger. So here is a design. We have A is 3 bits, E0, E1, E2, and B is 4 bits, B0, B1, B2, B3. You will have here a repetition, just instead of doing long wires, it will be messy. So instead of using this long wires and stuff, he just repeats the name, but you know in your mind that this wire here is connected to this wire here is connected to this wire, and so on. Okay, so these are not different; they are all the same. Good. So let's check what we need. We need many internal signals here. Okay. Again, our output is called the C, and is basically dependent on these internal signals. What are these internal signals? They are basically, these, multiplications. A0 B0, A0 B1, A0 B2, A0 B3, A1 B0, A1 B1, A1 B2, A1 B3. A1 B0, E2 B0, E2 B1, E2 B2, E2 B3. So you need these signals, these 12 signals. Okay. And as we see here in the design, so for example, the first bit of the output is basically E0 B0. The second bit is the first sum of this 4-bit binary adder, and so on. Another internal signals we need is this some signals. Look, because basically these are internal signals, and it's really obvious here because these are from something. It come out as a signal, as output from this adder here, and then it goes as input to this other here. So we need another signal to represent this sum here and this carry as well. Okay, so let's check how we do this. So for this, for example, for this, multiplier, these 12, multiplicators here, or multiplications, we're gonna, just like what we did with the second design that we explored in the previous video. We're gonna, implement or create a signal called the EB signal, which basically, you know, uh, 12 bits, okay, 11 down to 0. So I basically, again, I was doing the 4 by 4, multiplier first before doing that. So I didn't change. So, but basically you need only 12. If you do the 4 by 4 multiplier, you need 16 bits, 16 bit for the AB. As I said, I did the 4 by 4 first, so I just copied and pasted, so I didn't change it. But you don't. If you have extra signals that you are not using, that's fine. Okay. But what you need exactly is 12 bits, 11 down to 0. Okay. Let's go to discover. Now, I'm gonna call. Let's go back here to the signal. I'm gonna call this input here N0. Okay. And I'm gonna call this input here N1. Okay. And I'm gonna call this input here N3. Okay. So, and as you see, each one is 4 bits. Let's check first how we generate these 4 bits. Okay. These 11 bits basically. So again, like what we did with the 2 by 2 multiplier, we have the same, structure. I just changed this. This was I by 2. Now it's I times 4. Okay, and the 4 is the size of B. Okay, and I here basically because A is only 3 bits. So I is the counter for A, it is 3 bits, so 0 to 2. Then J is the counter for B, B is 4 bits, 3 down to 0, so 0 to 3. Okay, and again, these signals, we can take examples. When I is 0, this will be 0 multiplied by 4, which is 0 plus J. So when I is 0, this will give us AB of 0, AB of 1, AB of 2, AB of 3. And this AB of 0, 1, 2, 3 is basically A0. Let's go back here. A0, B0, A0, B1, A0, B2, A0, B3. When I is 1, this will give us A1, B0, A1, B1, A1, B2, A1, B3. When I is 2, this will give us the last row here. Okay? And I write it as a comment for you here. Look, this is basically the first 4 bits, second 4 bits, third 4 bits. Okay? Now, let's now construct the outputs. Look at the outputs here. So C0 is basically E0, B0. Okay, I call here the output M, multiplication, or you can call it whatever, not C. So now you know that C is basically M. So M of 0, the first bit of the output, AB of 0, which is A0, B0. Look, AB of 0 is A0, B0. Now, we're gonna construct this adder here. This adder has 2 inputs. I called the first one N0. I just create a signal called N0, this signal here. And the second input is again 4 bits, which I call N1. So what is N0? N0 basically is these, 3 bits, and the 4 bit is 0, 0 all the time. 0 all the time. So look, N0 from 2 down to 0, I mean 2, 1, 0, 2 down to 0, 2, 1, 0 is equal to EB of 3 down to 1. Okay, you can do it also 0 up to or 0 to 2 and AB 1, 2, 3. You can do that. 1, 2, 2 not 2 the number, 2 is TO. Okay, but usually in VHDL we prefer down to from something down to something. Good. Now, and the last bit of this input called IN0 is basically 0. Good. That's very good. That's very nice. Okay, so we constructed the first input N0 here. Now the second input. This is really easy. So this N1, it's 4 bits. It is basically these 4 bits. So N1 3 down to 0 is basically AB, the signal, 7 down to 4. 7 down to 4. Okay, this you can do it, one by one. You can say that N1 of 0 is basically AB of 4. N1 like this. N1 of 0, AB of 4. 0, 1, 2, 3, 4. Okay, you can say N1 of 1 is AB of 5, and so on. But this is just one line, can save you a lot of time. A lot of time. And a lot of errors as well. The simpler the code, the less the errors. Okay, now we have the two inputs ready. Then we can do the other here. So I have the rebel carry other as a package. So I instantiate the package in here. I'm sorry, I added the package here, or the library with the package here. Then instantiate it. This package takes two inputs, N0, N1, the second input here. The output sum and the carry. And in this design, we have two outputs, and I define the first the sum, then define the carry. The sum is 4 bits, and the carry is 1 bit. So S0, this output here. Okay, not S0. I mean by S0 the total sum, the 4 bits together of the first other. Okay, and C0. C0 is basically this carry here, this one. Good. And don't forget now that M of 1, this bit here, C1, which I call here the output M. So M of 1 is basically the first bit of the sum output of this other. So M of 1 is basically equal to S0 of 0. Okay? This is 0, the sum is 4 bits. The first bit goes to C1 or M1 here, M of 1 here. Good. Now the second addition here. The second addition needs only one variable. Let's call it N2, or I think I call it here N3, but that's just a name. Okay. So N3, I call this input N3. Is also 4 bits. These bits is basically, look, A2B0, A2B1, A2B2, A2B3, which is basically the last 4 bits of AB. So N2, N3, 3 down to 0 is basically AB, 11 down to 8. AB, 11 down to 8. Okay, that's very nice. Now, what is the first input? The first input is basically these 3 bits of the sum that we already have, S0, and the carry bit. So N2, okay, N2, another, so I call this input here, I call this input the agent, I call it N2. N2, 2 down to 0 is basically S0, 3 down to 1. Or you can name it like this, N2 of 0 is basically S0 of 1. N2 of 1 is basically S0 of 2. N2 of 2 is basically S0 of 3. You can do, but of course, this is, just one line saves you a lot of time. And then the final bit number 3, or the 4th bit of N2 is basically C0, this carry here of this binary other. Now the 2 inputs for this other is ready. N2 here and N3 here. Okay? And what are the outputs? Again, you have a sum. I call it S1. It's also 4 bits. And the carry, I call it C1. Now let's check, because now we have everything, So C2, which is basically M of 2, is basically sum of 0. And the M of 1 is C of C3, which is basically M of 3, is basically S of 1. And the C of 4, or M of 4, is basically S of 2, is 1 of 2. And basically, finally, not finally, M of 4 is basically, C5, or M of 5 is basically S1 of 3. The 4th bit of S1. So you can say basically that M, 5 down to 2, 5 here to 2 here, is basically S1, 3 down to 0. And finally, the carry is basically C of 6 or M of 6. Okay. So you need to study it. You need to study it, and because you have a lot of signals. I understand. But it's really easy. It's not complex. It's just need a focus and concentration, not to connect something in the wrong place. That's it. But it's not difficult at all. Okay. Now let's simulate it. So simulate multiplier 4-bit, 3-bit test bench. This one. Okay. And here you will have a higher number of cases because the final is 105. So you have a lot of cases basically. So we're gonna increase this to 100. And if we needed more, we just make more. Simulate again. Gonna change it to unsigned as usual. Zoom out a little bit. And now let's run. This is not the end. So because we should look, A is changing from 0 to 7, B is changing from 0 to 15. So the final output should be 15 by 7. So this is not, this is 7. So let's run for another 100 nanoseconds. Looks like this is the end. Yeah, look, 15 by 7 is 105. Okay, now we have all the cases, but it's not, it's clear. 0 by 0 is 0, 0 by 1 is 1, 0 by 2 is 0, 0 by 3, and again, we need just a little bit of zoom out. Then 0 by 8 is 0 by 15 is 0. Then 1 by 1 is 1, 1 by 2 is 2. You see, it looks like it's correct. 2 by 2 is 4, 3 by 2 is 6, 10 by 2 is 20, 11 by 2 is 22. 2 by 15 is 30. Looks like it's good. Okay. 3 by 3 is 9. 15 by 3 is 45. Let's take some higher. Okay. 9 by 6 is 45. That's right. 8 by 6 is 48. 6 by 6 is 36. 6 by 10 is 60. 15 by 6 is really 90. That's right. Okay, and now 15 by 7 is 105. I'm sure about that. Okay, and you see here, since we are multiplying all the time by 7, and this is incrementing by 1, 7, 8, 9, so you will see that the difference all the time is 7. So 49 plus 7 is 56. So it looks like it's correct. It's not look, it's correct. I know that. Okay, guys, that was the design of the 3-bit by 4-bit binary multiplier. Thank you very much for watching this video, and see you in the next video. Bye-bye.